Hello and welcome to the 6th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. We were in the middle of answering this question that if we have two behaviors given by two kernel representations here, we have seen that if the two matrices are related with each other by a unimodular matrix, then the two behaviors are equal, which also meant that if the row spans are equal, then the behaviors are equal. So, it is a sufficient condition. The question that we were in the middle of answering was the following, that can we exploit this idea of unimodular relation between two such matrices? Can we exploit this idea to obtain representations which are in some sense more useful? This of course is reminiscent of the row operations that we do when we are dealing with constant equations, as opposed to differential equations. We do row operations and obtain matrices in the form of a row reduced echelon form when we are dealing with systems of linear equations. Can we do the same thing for systems of ordinary differential equations, linear with constant coefficients, and difference equations, linear with constant coefficients? We looked at one example and there we saw that we could actually do something which is very similar to row operations. The only added feature there was that for each row operation we had to make sure that the row operation is encoded, it is possible to encode the row operation by a unimodular matrix. But that was only an example. Let me recall the example for you. We looked at these two equations, xi square plus 3 xi plus 2 and xi squared plus 4 xi plus 3, and we saw how this can be converted to this by unimodular row operations. But this was only an example. Can we do it in general? That is the question that we are asking. Okay. All right. So, now let us look at this particular situation. So, we are going to look at this particular case, case 1, which is a very special case, and then we will see what we can do for the general case. Case 1 is the case of a finitely many polynomial. Suppose I have P1 xi all the way up to PR. Should I use R? Should I use something else? Let me use G, because anyway that is the number of equations we have. So, we have this collection of polynomials, right. So, this is just a column vector R G cross 1 xi. Okay. Is it possible to convert this into the form of a column vector which looks like this? Is it possible to somehow go from here to here through unimodular row operations? The answer is yes, and this is true because of Bezout Aryabhatta or Aryabhatta-Bezout identity. That is what we are going to see. And in fact, let me just give you an idea, tell you beforehand that this f, I am sure many of you are able to already guess what this f is. This f actually turns out to be the GCD of these polynomials. The greatest common divisor. Let us see how we are doing it. So, our starting point. So, this is going to be explained in the form of an algorithm. This is just Euclid's division algorithm, but we are going to we're going to sort of encode it as unimodular row operations, so that it becomes useful for us, yeah, so that it's tailor made for our purposes, and also it's easier to see why this is true if we do it algorithmically. Okay. All right. So this is our starting point. Step 1. First, what is the input? What is given to us? Input, of course, is this collection of polynomials p1 psi up to pg psi. What is step 1? Step 1 is permute these polynomials so that the one with the least degree appears at first. So multiply by a permutation matrix. Permutation matrix, of course, is a unimodular matrix because it's a constant matrix with non-zero determinant. Therefore, the determinant is a constant. So that when we do this, I am going to get rid of the argument now because it's understood that these are polynomials p1 up to pg, and the product is, yeah, the result of this product is p1 tilde up to pg tilde. You see p1 and p, p1 and p tilde, p polynomials and the p tilde polynomials are exactly the same polynomials, just the indices are different. The degree of p1 tilde is less than or equal to the degree of pi tilde for all I. That's the condition. Okay. Now, what do we do? What we do next? We just do division with remainder. That's it. Now, when does the division? What is the speciality of division with remainder? If you take two polynomials p and q. If you take two polynomials, let me write here. If you take two polynomials, this is division by division with remainder. Yeah. So take two polynomials p and q. When you do this division by remainder, what you get is, suppose degree of p is less than degree of q. So degree of p is assumed to be less than or equal to degree of q without loss of generality. Then we divide q by p. So q can then be written as p times a plus r. This is the remainder, and the condition for this to be the remainder is that degree of the remainder is strictly less than the degree of the divisor, that is p. That is how you do division with remainder, right? I hope you remember. So our step 2 is this. So divide p2 tilde by p1 tilde, because p1 tilde has degree less than or equal to p2 tilde. This is a division with remainder, and the remainder will have degree strictly less than the degree of p1 tilde. So, and we encode this in the form of a unimodular operation p1 p2 tilde dot 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 up to pg tilde. We encode this in the form of a this is still 1. It's the first iteration. Yeah, we encode this in the form of unimodular operation. What does the unimodular operation do? You see, the unimodular operation keeps the first row intact. So the first row is unchanged. That's why the first row of the unimodular operation is just 1 and zeros. What is the second row of the unimodular operation? The second row is changed by the second row minus the quotient time the first row, right? and that is going to be some polynomial here. I am going to write just a star here because this star is possibly a non-zero polynomial. Yeah. Everything else remains the same, and then from that point onwards everything remains the same also, right? So I hope you see what is going on here. This is just an identity matrix, yeah, perturbed by only one other entry, namely the 2 1 entry, which is a possibly non-zero polynomial. Non-zero polynomial. I am sure you can see that this is a unimodular matrix because it is just a lower triangular matrix with ones on the diagonal. The determinant is obviously 1. That is my step 2. What is the answer of the step 2? Answer of the step 2 is P1 tilde 1, P2 tilde 1 and so on up to Pg tilde 1. You see from the P3 tilde onwards it remains the same. In fact, P1 tilde also remains the same, only this P2 tilde is the guy that changes to something whose degree is strictly less than P1 tilde. Okay. What is step 3? I hope it is understandable what step 2 is. What is step 3? Step 3 now is anybody's guess. Okay. Step 3 will be changing the third row exactly the way we have changed the second row. Okay. So the first and second row remains the same, only the third row is changed by division by the first row again, by P1 again. So P3 tilde gets changed by P1 tilde times something, P3 tilde minus something times P1 tilde, and that will be the result of this division is the remainder. So the third entry will change. So once again this is a perturbation of the identity matrix by just this entry, namely the 3 1 entry that acts on this polynomial P, and it changes to P1 tilde, P2 tilde and P3 tilde is the one that changes. Everything else remains the same. Okay. I hope you understand what is going on, and I keep doing this till step G. Okay. So till step G I just use the first polynomial to do division with remainder to change the second, third, fourth and so on, all these polynomials. Okay. Now what is the outcome of that? So outcome of step G is a collection of polynomials, yeah, namely once again let me use P1 up to what should I use? Should I use G? I think G should be fine. To PG, I have gotten rid of the tildes. I hope you don't mind that. So this is the outcome of the polynomials after the gth step. What happens then? In the gth step, you see every entry starting from 2 onwards, all these polynomials have degree strictly less than the degree of this guy, which then means if I now search through all these polynomials and find out the guy with least degree, that least degree is guaranteed to be less than, strictly less than the degree of this guy, unless all these polynomials have become zero polynomials. Unless they are all zeros, there will be at least one guy whose degree will be strictly less than the degree of P1. Yeah. So once again I do a permutation and bring that guy to the top, the least degree guy to the top. That is my step G plus 1. Step G plus 1. If P2G up to PGG are not all zeros, then find the one with the least degree and bring it to the top. Okay? You see, if all these polynomials were 0 in fact, then I actually would have achieved my goal. I would have had a series of pre-multiplications by unimodular matrices, so that the result is just a non-zero polynomial and all zeros. Yeah? Remember, this is the one that I wanted to achieve. This is the structure that I wanted to achieve. Yeah? But if not all of them are 0, then I do this step g plus 1. And then I just go back to step 2. I just go back to step 2 and repeat what I was doing. Go back to step 2, go back to step 2 and repeat. What does that do? What does that mean? If I go back to step 2 and repeat, what essentially happens is that once again the degree becomes smaller. The degree will become strictly smaller than the top guy, which was strictly smaller than the guy I had started with, namely P1 tilde. Yeah? And once I am done with it, once I have step 2g, yeah? In fact 2g plus 1 perhaps, I mean g added to this guy, 2g in fact. After the step 2g, yeah, 2gth step, yeah, what happens is that now, barring the first guy, I have these other second starting from index 2, 3, 4 up to g. All these guys will have degrees strictly less than the degree of the first guy, which was once again strictly less than the degree of the guy that I had started with. So that means after all these g number of steps, the degree strictly decreases unless all the polynomials have become 0. As long as at least one of the polynomials is non-zero, the degree is guaranteed to reduce. Okay? So once again, if there are at least if there is at least one non-zero polynomial, I find out the least degree among these guys starting from 2 to g, and then once again I bring that guy to the top and I repeat. Go back to step 2 and repeat. And I keep doing this as long as there are non-zero polynomials below the first guy. I will be able to keep on repeating this, but once again I cannot keep on repeating this forever, because the degree is strictly decreasing and the degrees of polynomials are bounded below by 0. The degree cannot be less than 0. So here are these positive integers, non-negative integers, which are the degrees. That degree is decreasing. So if I just take a snapshot of my, like if I write a code, then after each of these g steps, after you have done the permutation, find out the degree of this guy. This degree is supposed to decrease, strictly decrease after each cycle. Yeah, but can it decrease indefinitely? It cannot. Of course, it cannot decrease because the degree is lower bounded. Let me write that in bold, big letters. Lower bounded by 0. It cannot go on forever. So then, now just think about it. As long as these guys are non-zero, it means I can continue, but I cannot continue forever. So that means these guys cannot remain non-zero forever. So all of them will become 0 after finitely many steps, right? And at each step, multiplication is by a unimodular matrix. So that means I actually have a finite series of unimodular pre-multiplications, pre-multiplications by unimodular matrices, so that when this multiplies to the polynomial, collection of polynomials, let me not call it R, this was my original collection of polynomials. After finitely many such unimodular multiplications, pre-multiplications, it should definitely change to this form. Yeah, just club these guys together and call it U. This product, these are unimodular matrices, so their finite product is also a unimodular matrix. So we ultimately have a unimodular matrix U xi multiplying the given set of polynomials P1 xi up to Pg xi, resulting in a polynomial which is f xi and all zeros. Let me write P2 xi as well. Great. Okay. Now, what does this tell us? What does this tell us? Well, some side informations. I mean, about what it tells us. Okay, U xi is actually U11 xi, U12 xi, dot 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 up to U1g xi, right? This is the first row of U, and then of course there are these other entries as well. But this is important for us because what we know now from this is the fact that this is equal to f xi and all zeros. So when we do this first row, the product with the first row, that's like a dot product, that must be equal to f. So f xi then is equal to a linear combination of the given set of polynomials P1 xi plus U12 xi P2 xi plus dot 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 plus U1g xi Pg xi, right? Okay. Not just that, it also means that because U is a unimodular matrix, U inverse xi is equal to U inverse xi multiplying f xi and all zeros. This must be equal to P1 xi, P2 xi, dot 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 up to Pg xi. Okay. But what does this mean? This is f and all zeros, right? So that means when you do this multiplication, it just chooses the first column of U inverse xi and multiplies it by f. So I have V11 xi, that's the 1 entry of U inverse. V21 xi, that's the 2 entry of U inverse, dot 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 Vg1 xi. This multiplying f xi must be equal to P1 xi, P2 xi, dot 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 Pg xi. Wow. Now let us concentrate on this equation, call it 1. This one equation tells me what? F divides P1, P2 and Pg, isn't it? Because V11 is a polynomial times f is P1, right? V11 times f is P1, V21 times f is P2, likewise Vg1 times f is Pg. So f divides Pi for all I. That means f is a common divisor. Great, no? Now, look at this equation. Let me call this 2. Suppose there is another common divisor D. Suppose, where should I write? Suppose D divides Pi for all I. That means I should be able to write Pi as some D times Qi. But then look at this. So f is equal to U11 P1 xi. But that means this P1 I will write Q1 times D. This P2 I will write Q2 times D. Likewise, this PG I will write QG times D. D is common, I will just take D out common. That will mean F is equal to summation U, let me check what for the indices, 1I xi times Qi xi, I going from 1 to G times D, D xi, F xi. You see, then D divides F, D divides F, which means the moment I assume D divides, D is a common divisor, that means D should divide F as well. So that's the definition of greatest common divisor. So that means F is the GCD. Great, no? So what we have essentially proven here is that by doing these unimodular row operations, we can convert this collection of polynomials P1 up to Pg into this, where this guy is the GCD of these polynomials. And that's Aryabhatta-Bezout identity, that the GCD can be written as a linear combination of the polynomials. Yeah? It's usually stated in terms of two polynomials, given two polynomials P xi and Q xi. Suppose GCD is F xi, then this implies there exists a polynomial A xi and a polynomial B xi such that A xi P xi plus B xi Q xi is equal to F xi, the GCD. This will become exceptionally useful for us. In fact, it's more so when we have P and Q to be co-prime. That means when the GCD is 1, right? There's only no non-constant common divisors. In that case, Bezout identity means that the linear combination will give us 1. Okay. In other words, for co-prime set of polynomials, there will be unimodular operations which convert this to 1 and all zeros. That will be particularly useful for us. Now, where do we take it from here? This is, let me mention, this is the AB identity that I have been mentioning, Aryabhatta-Bezout identity. Okay, now, where do we move from here? You see, now suppose I have a polynomial matrix as opposed to just one collection of polynomials. This is, you see, like this, no? Dot dot dot, then other entries dot dot dot, 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 like this. This is my matrix R. Okay. Now, I just concentrate on the first column. Unless the first column has only zeros, it's a collection of non-zero polynomials which will have a GCD. I know for a fact now that I can multiply this by a unimodular matrix U0 such that when I take this product, I don't bother about what is happening to the rest of the columns, but the first column I know will convert to some F1 xi and all zeros, right? And this is possible as long as one of the entries in this first column is non-zero. If it was a 0 column to start with, then we just move on to the second column. Yeah. Otherwise, this is what I have. Okay. And the remaining are some entries. I don't worry much about them, at least at this point. But the first one changes to something like this. Now, I look at this block. And in this block, once again, I do the search. Whatever I had done with this entire matrix R, now I do exactly the same thing with this smaller sized matrix, which has lesser number of rows, lesser number of rows and lesser number of columns, less by 1, right? I look at this block. Once again in this block, if all these entries are 0, then I just don't do anything. I move on to the second one. Yeah. If not, then I just do the same thing. Now here I will take unimodular matrices of size g minus 1 by g minus 1, right. I will just pad it with 1 and zeros in the first row and the first column, so that this becomes a g by g matrix, and that I will multiply to u0 xi, r xi, and the result will be that this will be f1 xi. This is all zeros, yeah, unless these guys are all zeros. Suppose assume this is 0. Next guy I will do this, that okay, this guy is here, something other than f2 xi, and then all zeros. I am sure you see the pattern emerging. Yeah, how does this look like? This finally is going to look like an upper triangular matrix like this, with these being 0, these being 0, right, such that these diagonal entries are non-zero polynomials. Yeah, these I will just count these number of non-zero polynomials in the diagonal, and that will be the rank of the matrix. Yeah, sounds exactly like row reduced echelon form, isn't it? Yeah, but remember that this is not, these matrices are not constant matrices. So whatever row reduced echelon form we got in our linear algebra course by doing elementary row operations, they are not allowed here. These are polynomials. I have to work with polynomials here. But still, because of Aryabhatta-Bezout identity, I can do this polynomial row operations, yeah, and convert this matrix into an upper triangular matrix like this. Importantly, a matrix with whose rank can be read off from the matrix itself. Okay. Now, as far as these 0 rows are concerned, you see, ultimately we are dealing with differential equations, right? And these 0 rows just mean nothing. Yeah, they just don't give any equations at all. This just says that 0 times w is equal to 0. They are non-equations, in fact. No informations are given. So I might as well concentrate on this part, yeah, which has these diagonal entries there, whose the number of rows is equal to the rank of the matrix. Such a thing will be called a full row rank matrix. And from now on, we will use this property quite regularly, that when we talk about a behavior being given by an R xi matrix, kernel of an R xi matrix, we will assume that this is a full row rank matrix, full row rank matrix. Can we obtain that? Yes, because by doing unimodular operations, you can convert it to full row rank. Okay. Now, where do we go from here? Yeah. And more importantly, this question that okay, if the row spans are equal, they are related by unimodular transformation, then the behaviors are equal. Yeah, is it enough? It's a sufficient condition. Is it also necessary? What does the C infinity has? Has C infinity got to do with this? All these questions and many more, importantly, elimination theory and how one uses elimination theory. How does one come about elimination theory of eliminating latent variables? How, and more importantly, how we get these ideas of eliminating variables, yeah, obtaining solutions, projecting solutions. How these ideas, which are very analytic ideas, how they are obtained through sheer power of algebra, is something that we will see in the next few lectures. Okay? Till then, take care of yourselves, and bye from my side.